Hi, welcome back. This is our first official lesson. Hopefully, it's mostly review for you, but I did think it was important to kind of quickly go over to make sure that we're all starting out on the same page. So I'm going to move right on. This lesson is coming to you from chapter 1.1 and 1.2 in the textbook. As I mentioned in class yesterday, I'm going to try very hard to stick with the textbook and follow along with that. So you should be able to either read then listen, or listen then read, or whatever works for you. So the point of this lesson is really just to give you an overview of, or an introduction to some of the basic kind of terminology that we're going to use. Alright, so this idea of a system. We went over this in FABE 325, and it's probably a concept that you've seen over and over again in your engineering courses. But when we talk about a system, it's really what you define your system to be. So we use these blocks diagrams in 325, and we have an input and an output. And our system is whatever we define it to be. So if we just have one entity, maybe this is, from 325, maybe this is a mixer. So we've got two different streams coming in, and then we have, a mixed stream coming out. So for this case here, we would define our system as being around this unit, and so it's clear the arrows coming through the dotted line are your inputs, and then the arrows coming out are the outputs. In 325 again, we started making things a little bit more complex, and maybe we added a second unit here. So we then could define our system to be either just the first little box here, or we could make it the entire system, and both of them would be the box. Both of them would be included in the system. As we go through this, you can define your system, and clearly there's some better choices than others, and the only way to figure that out is through practice. But really just making sure you define what your system is, and a lot of times drawing it out in this little block diagram form is the I don't want to call it the best, but it kind of helps to simplify things. So I've already used this term input and output in my definition of a system, but for the purpose of this course, the input, we'll call that the cause, and the output is the effect. So when we have something come into a system, it may there's something will happen. The system will behave. There will be a behavior that is exhibited by the system, and that behavior is generally the output, or it influences the output. In a static system, we can really define it as the input, the current value of the output is only influenced by the current value of the input. So I'm going to write that out here. I'm going to pause before I write so I don't use up time, and you'll have to let me know if that makes it easier or harder for you. Alright, so static current output only depends on the current input, whereas a dynamic system, the current output is dependent on all the previous values of the input, and I'll talk about that in just a sec. So if we go back to, I said the wheel, for example. A wheel would be an example of a dynamic system, in that the current rotation is not just dependent on what the force is right this very minute, but also what the force was over the last couple of minutes. And if you think about yourself riding on a bicycle, how fast that wheel is spinning is not really dependent on how hard you're pedaling right now. If you've just went down a hill, the previous values of that input will make you go faster right now, even though you may not be putting in the same amount of effort. So the dynamic systems, we can approximate that, or not really approximate, but we can kind of maybe make it a little bit more simple to understand by saying it varies with time. And the reason I kind of hesitate on giving you that definition is a dynamic system can stay at a steady state. So, for example, I think yesterday I used the example of the thermostat in your house. So as you change the thermostat in the house, it doesn't instantly heat up. So if you go in to turn your thermostat up to like 75 degrees, your house isn't instantly 75 degrees. There's kind of a variance with time. However, once it gets up to 75 degrees, it kind of usually stays there. Just because it's staying there doesn't mean it became a static system. If you had some kind of an outside influence, if somebody opens the window or if somebody turns down the thermostat, it's going to start varying with time again. It's going to kind of fluctuate. So there are no real true static systems. An example that they use in the textbook is a resistor. And if we think back to your circuits course, you've got a resistor, there's a current going through the resistor, and if we talk about Ohm's law, the voltage is equal to the current times the resistance. So in this case, the voltage is the output, the current is the input. Theoretically, that resistance is constant, so whatever the current input is, whatever the current is, that's confusing, there you can tell what the output of the voltage is going to be. If the current changes, the voltage changes, and it doesn't really fluctuate with time. Now, when I said there's no true static systems, we do know that if we increase the current, then you're going to increase the temperature. Of the resistor. As soon as you increase the temperature of a metal, it causes a decrease in the resistance. So all of a sudden, it's not truly a static system. If the current has been really high in the past, you're probably going to be influencing that resistance, and there's kind of an effect there. But when we talk about a static system, we're usually approximating, and it is reasonable in a lot of cases to approximate something using that. But for the purpose of this class, we're really talking about systems that vary over time, and we're talking about modeling and characterizing how they vary over time based on certain changes in their input. So that brings us kind of this last term here, and really what we're trying to do when we model is really simplify the problem down into kind of these blocks. So we're trying to simplify the problem down into little blocks and then apply fundamental principles. And we've done an example, or we talked about an example in the previous section here about electricity. So one of the fundamental principles that we might apply is electrical principles. We could also talk about thermal principles. So we'd be talking about heat transfer, that sort of thing. Or mechanical principles, maybe like Newton's first law, first or second law. There's any number of mechanical type properties, including fluid mechanics, that sort of thing. So really, modeling is just applying fundamental principles and generating some kind of a mathematical equation that relates the input to the output. So the textbook uses the SI system and this thing called foot-pound-second system, which is kind of similar to the American engineering units. It's not exactly the same thing, but it's close enough. This course is not a units conversion course. It is not. That's not the point, I guess. You do need to know how to use unit conversions, and for those of you who have not had me before in class, I am not a very big proponent of memorization of things. So unit conversions is another example. It's silly to try to memorize all of them. And I will give you unit conversions anywhere that you need them on an exam or anything like that. So it's important that you know how to apply a unit conversion, but not necessarily that you memorize all of them or anything like that. So take a look at them, make sure you kind of familiarize yourself, especially with the difference between mass and force. Make sure you're kind of clear on that. That's something that we'll use routinely throughout the class. So I'm going to sign off here. Thank you again to everybody who's put comments on Carmen, and please check the Carmen site routinely and actively participate in those discussions. I think you'll find that very useful and helpful for your progress in the class. So thanks, and I'll talk to you soon. Bye.